Hi class, today we're going to be discussing limiting reactants and percent yield. So a limiting reactant is a reactant in a chemical reaction. So far we've been learning how to balance reactions. We've worked with moles, molar mass, and mass. Now we are going to determine something else. What that's still related. So up until this point, we've just been working with the numbers that have been given. But the reality is in chemistry, a lot of reactions do not happen, or they do not happen very clean. There's a lot of impurities, there's a lot of side products, there's a lot of things that just go wrong. And the amount that would be produced on paper is not what matches in the lab at all, believe me. And so we've come up with a way to determine how successful a reaction is. So if you're in an organic lab, the number one thing, so when you're in an organic lab, you have to present your work weekly and or monthly, bi-monthly, depends on what lab you work in. And you will have to show reactions. And when you do, the first thing that will always be asked if you do not address is, what is the percent yield of this reaction? And that is how successful, out of 100%, how much was produced. It's a big deal. So in order for us to get there, we have to look at limiting reactant. So this is something that I'm sure all of us have encountered. If you've ever wanted to eat something, you might find one object, but you need something else, and that is either little to none. For instance, cereal. You want cereal? There's not enough milk for cereal. That's what we're dealing with here. So if we look at this picture here, we have hot dogs, we have a hot dog buns, and then we create a hot dog in a bun. You have 3 hot dogs, but we only have 2 buns. This means that we can only have 2 hot dogs in a bun, leaving 1 hot dog left over. The limiting reactant is the substance that it gets used up first. So in this case, it's the buns. We run out of buns before we run out of hot dogs. So that is the limiting reactant. It controls the reaction. It controls this putting together this food. That controls it, because once you run out of the buns, it stops. There's no more hot dog in a bun. And the excess is whatever's left over. The substance left over, in this case, that's a hot dog. So here, if we wanted to make a peanut butter sandwich, you need 2 slices of bread and 1 tablespoon of peanut butter. And if you look here, some examples. 1 loaf has 20 slices, but you only have 1 tablespoon of peanut butter. You can only make 1 sandwich. So this means that the limiting reactant is the peanut butter, because that's it. You now have just a bunch of slices of bread, but no peanut butter. So the bread is the excess. But let's say we have 4 slices and 1 full jar of peanut butter. Now it's the opposite. We can have 2 sandwiches made. The limiting reactant is the bread, because we've ran out of bread, and the excess is the peanut butter. 8 slices, 1 full jar. We can have 4 sandwiches, but the bread will still run out before the jar of peanut butter is done, depending on how thick and how much you use that peanut butter. But if we go by 1 tablespoon, that means that the bread is still the limiting here, and the peanut butter is the excess. So what we need now to do from balanced reactions is we have to identify a limiting reactant when we're given the quantities of 2 reactants. So this is the tip here. When you're given a word problem and you're given 2 reactants, the quantities, that's a limiting reactant problem. And I'll point that out again. Then from there, we figure out a percent yield. So calculating moles of a product from a limiting. In many reactions, there's a limiting reactant that determines the amount of the product. So in most cases, we don't talk about it except specifically when we're dealing with limiting reactant reactions. But there's always one that will run out before the other. Just happens. That's no matter how well you plan it. Given a chemical reaction, from each reactant, we can calculate the amount of product possible when it's completely consumed, then determine the limiting reactant. That's the one that runs out first and produces a smaller amount. So what we'll do, and if we take a step back, here is you're given 2 quantities of reactants. You have to calculate, go through the reactants of whatever it's being asked for on the product. So basically go from A, working with A, and determining the mass of B or moles of B. But you're doing it with 2 reactants. And the one that produces the smaller amount, that is the limiting reactant. May not make sense. Let's do a problem. So if you have 3 moles of carbon dioxide, I just fixed this and this must not have been the same problem. If 3 moles, this is CO, it should be CO. I fixed it, but I think I fixed it on another slide. If 3 moles of carbon monoxide and 5 moles of hydrogen gas are the initial reactants, how many moles of methanol can be produced and what is the limiting reactant? So the hint here, and it won't always tell you that it's a limiting reactant problem. It might say it in different words. The hint is you're given both reactants. You're given amount to both of these because you need them in order to determine how much each one will produce of the product. So given here are reactants, we need to know how many moles of methanol can be produced. And we're going to need to know mole to mole factors with this, with the given equation. So here is, we have a plan. We have 3 moles of CO and we have 5 moles of hydrogen. So for both of these separately, we have to work out this problem. Yes, it's a time-consuming process. We will use the moles of CO and we'll do a mole to mole factor and we'll determine how many moles of methanol with carbon monoxide, and then we'll take the amount for hydrogen and we'll do the same thing and we'll see how many moles are produced from each part. So in this case, we use our conversion. So we have 1 mole of CO equals 1 mole of methanol. And in this one, we have 2 moles of hydrogen equals 1 mole of methanol. And then we set up our conversion factors based on that information. So now, you would have to work on one first and then work on the second one. But this is the way they set this up is on one page. So here we have 3 moles of CO. And we have 1 mole of CO, carbon monoxide, and 1 mole of methanol. This ends up producing 3 moles of methanol. Now, we need to know the product, how much we produce from hydrogen. So 5 moles of hydrogen is what it was given to us in the word problem. And here we have 2 moles of methanol based on the problem, and 2 moles of hydrogen and 1 mole of methanol. And that produces 2.5 moles of methanol. So you have to do these steps. They never change for limiting reactants. You're given the amount of both reactants. You have to separately determine what is produced by whatever product is given to you. And then the smaller amount is the limiting reactant. It's the one that will run out first, leaving the other one as excess. So in this case, hydrogen, and don't go by the numbers. The numbers are very deceiving. So this one is the limiting reactant, meaning that the carbon monoxide is left in excess. There will be a amount of carbon monoxide left over after this reaction has been done because it has no more hydrogen gas to use. So only 2.5 moles of methanol is produced. And I changed the way that they have it listed. This is normally how it should be listed. Well, how I know it, and they have it listed as this. It's the same thing. Okay, so let's go on and go into this a little bit more. The quantities of reactants can be given in grams. So we just learned it in moles, but we can also do this in grams. And that just means one more step of converting using the molar mass step. So we convert the grams of each reactant to moles of reactants. So in this case, they're saying that they will give it to you in grams and you have to do all the steps. So we're doing extra on both sides. So convert the grams of each reactant to moles and then using the molar mass conversions. Then we use the mole to mole factors to convert the moles of reactant to moles of product. And then we use the molar mass to convert the moles of product to grams of product. Everything we've already been doing previously has been built up to this. The reactant that produces the least amount is the limiting reactant. So let's do a problem. So here is silicon carbide. Carbide is a ceramic material that tolerates extreme temperatures and is used as an abrasive and in brake discs of sports cars. How many grams of CO are formed when 70 grams of silicon dioxide and 50 grams of carbon? Oh, sorry, that's I heard my phone. And 50 grams of carbon. So here we have is the balanced equation, and we are given both reactants. So this is a limiting reactant problem. You see, this question does not state anywhere what the terms limiting reactants, so it might be deceiving. So you have to specifically look for certain things. And in this one is you're given 70 grams of silicon dioxide and you are given 50 grams of carbon. Both values for reactants. So that is telling you this is a limiting reactant because it's asking you how much of carbon monoxide can be produced. So here I pulled out the amounts like I always do when I'm working on balanced equations so I can see what I have. Carbon monoxide is the one that we need to know how much is produced. So our given is here. We need to get to grams of carbon monoxide, and we're going to have to use the molar masses and mole to mole factors based on this equation. So again, here's my hint. If you're given both amounts of reactants, it's a limiting reactant problem. I skipped a slide. Okay, so here is the same. We're just doing this, expanding on two more steps. So we're starting out with grams for both of these. We have to use the molar mass for each one. Then we get the moles of each one. Then we look at the mole to mole factor, and then the moles of CO, molar mass for the product, and then grams of the product. And you'll do the same exact steps for each product, each reactant. The only difference is you'll use the molar mass for this one, the molar mass for this one, and the mole to mole ratio may be different. So for instance, silicon dioxide has a 1 in front, but carbon has a 3. So this is a 1 to 2, and this is a 3 to 2 ratio. So those, you have to make sure you factor in those little things that if you don't catch, messes up the whole problem and your answer's wrong after all that hard work. So here we pull everything out. We get our molar mass. 1 mole of silicon dioxide is 60.09 grams. 1 mole of carbon is 12.01 grams. And then we set it up in conversion factors. And we have one more. We need the product because this answer needs to be in grams. So we have 1 mole of carbon monoxide and we have the mass of it. And then we can set this one up also in a conversion factor. So now, same steps for both. We have to figure out which one is the limiting. It will always be the smaller amount, and we need to know which one that is, but we go through the same thing. So 70 grams of silicon dioxide. We use our molar mass, grams per mole, and this can cancel out. And this leaves us with 1 mole of silicon dioxide. This is our ratio from the balanced equation. It leaves 2 moles of carbon monoxide, and now we use our molar mass for carbon monoxide, and this produces 65.3 grams of carbon monoxide. And then you can see the exact with the 4 sig figs, exact. And we do the same with the bottom. 50 grams of carbon, and we want to get rid of grams of carbon, so we got to do 1 mole, and molar mass is always 1 mole. Then we do the ratio for the balanced equation, 3 moles of carbon to 2 moles of carbon monoxide, 1 mole of carbon monoxide to the molar mass of carbon monoxide. And then we can cancel everything that we don't want. We end up with 77.7 grams of carbon monoxide. 65.3 versus 77.7. So this being the smaller amount, this is the limiting reactant that will be produced. This is the only amount that can be produced. This will never happen because this silicon dioxide will run out well before it can ever get to this. Okay, so let's do another problem. Given the reaction, and here's the reaction, calculate the amount of ammonia that can be formed when 2.5 grams of nitrogen gas reacts with 2 grams of hydrogen gas. So the first thing I do, pull the problem down, pull out the information I need. Okay, and now this is a limiting reactant problem. Why? Because we're given values for both reactants. So let's see what we have. We need to go through the same steps for both, doing the same thing: molar mass, moles, mole to mole factor, moles of product, molar mass of product. And this is asking, if we need to look at it again, is calculate the amount of ammonia that can be formed when 2.5 grams of nitrogen and 2.00 grams of hydrogen. So this is asking for the amount, so it's mass. It's not saying moles, it's amount. And since these are in grams, this one's going to be in grams. So we write the plan out, went over that, and now let's just plug it all in. So we have 1 mole of nitrogen is 28.02 grams per nitrogen, and we can do our conversion factors for that. We have 1 mole of H2. Remember, these are gases. These are diatomic molecules. They exist in nature as two atoms together. They do not exist with just one. So you have to account for that. So this number here is for 2 nitrogen atoms. This is for 2 hydrogen atoms. And then we have our conversion factor set up in a ratio. And then we have 1 mole of ammonia. And this is the amount for ammonia. And we can set that one up. So now we're going to do... and it's doing the coefficients as well. Yes, we need those. I forgot. So if we look at the balanced equation, we have 3 moles of hydrogen to 2 moles of ammonia. We can see that there, and then we can set it up in the conversion factor. And then we have 1 mole of nitrogen to 2 moles of ammonia, and we can set that one up as well. So you have to do the exact same thing for both, using the amounts that are specific for that substance. So we have 2.5 grams of nitrogen, and we go through the molar mass of nitrogen. Then we take the ratio of the balanced equation, and then we take the molar mass of the product, which is ammonia. And this gives us 3.04 grams of ammonia. And then here we have 2 grams is what we started with. We go through the molar mass of hydrogen. We do the balanced equation ratio that we can see here. And then we do the molar mass of ammonia, the product, and we end up with 33.7 grams. So this is a very big difference from 33.7 grams of ammonia to 3.04 grams of ammonia. This is obviously the one that will be produced, but this is where I say do not look at the values and just assume that you're going to know. This is very deceiving. You have 2.5 grams of nitrogen and 2 grams of hydrogen, and 2 grams of hydrogen will produce this large amount, and 2.5 grams of nitrogen will result in a way smaller amount. So you have to work these out completely. Never look at it and think that you can figure it out. Does not happen, and it's usually going to be wrong. So I put arrows because this slide is so busy, so you can see, and I think I probably made it busier, but this is a smaller amount, so this is the amount that's the limiting reactant. So I want to point out again, I put it here. Do not ever look at these and think that you can figure out which one it is. Never going to happen. Very deceiving. Work it out. Work them both out. Yes, they take a long time, but this is something you have to learn. Now, as if that wasn't enough, we have to actually go on further. So most of limiting reactant problems go into theoretical and percent yield. So once you figure out the limiting reactant, you now will have to figure out the percent yield. And the percent yield is how successful a reaction was, and it's based on percent out of 100. So when the reaction does not go to completion, or some of the reactant or product is lost, the amount of product produced is less. And it is. I still work in a lab. It's always less. You will never get to 100%. Never. Theoretical yield is the maximum amount of product, which is calculated using the balanced equation. So the theoretical yield is the amount on paper. If you were to sit down before you start an experiment and determine based on the amounts that they've given you, on paper, this is the amount that can be produced. It's the largest amount that can be produced. Now, theoretical is under ideal, in an ideal environment, conditions. Nothing goes wrong. The air doesn't affect. The glassware isn't dirty. The Bunsen burner's perfect. Everything goes perfectly. And we are human. That doesn't happen. So this is on paper. Theoretical is on paper. What is the max amount to be produced? Actual is the amount that's in the lab. That's the amount that would be produced in the lab. So you're going to take those and you're going to set it up in a percent yield. And theoretical will always be the max amount. Keyword max. Actual should always be lower. If it's not lower, this percent is going to be over 100%, and that means that you have an impurity. You did something wrong in one of the steps. Something's going to go wrong to cause that's holding on to that impurity, and it's being factored into the amount that was produced, and that's wrong. So it should always be under 100, and actual should always be lower than theoretical. So if you're doing a problem and you're really confused about, well, I don't know if I'm doing actual or theoretical, you don't worry. Once you get to the end, you'll be able to compare the values and you'll be able to see, unless you made a mistake on experiments like over 100 something. I'll show you. So here, this would normally, actual, theoretical, they go with limiting. You usually have to continue on. It will be giving you more information, and you'd actually have to go on to percent yield. This is an isolated problem by itself, and we're going to just do it like this to get you into understand percent yield. On the space shuttle, lithium hydroxide is used to absorb exhaled carbon dioxide from breathing air to form lithium hydrogen carbonate or lithium bicarbonate. This is why you need to know polyatomic ions. What is the percent yield of the reaction if 50 grams of lithium hydroxide gives 72 grams of lithium hydrogen carbonate or lithium bicarbonate, depending on how you want to say that. So here I've pulled out all the information that we need. Nowhere in here does it say what the actual is. But if you get confused, don't worry about the actual yield yet, because if you do the calculation correct on paper, you'll be able to see which one it is. Actual is always lower than theoretical. But in most cases, you are always calculating the theoretical yield, and they will always give you the actual because you're not in the lab. So that's what this is saying. What is the percent yield of the reaction? If 50 grams of lithium hydroxide gives 72 grams of lithium hydrogen carbonate. So it's telling you what was given. Okay, so let's go on. We need to determine the product. So we need to determine how much was produced theoretically. So they've given you what was actually done in the lab. Somebody did this in the lab and they produced 72.8. Now, we need to determine the theoretical. So you should understand that this should have an amount larger than what was given. So we expect a value larger than 72.8. So we're going to start out the same way we've started other ones. Grams of reactant, molar mass, moles. We do the mole to mole factor, looking at the equation, moles of product, molar mass, and then grams. And then we'll have our amount to plug in, the theoretical yield, to plug in here, and actual will go here. So let's take a look at the coefficients, the mole to mole factors. So we have 1 mole lithium hydroxide gives us 23.95 grams of lithium hydroxide. We can do the conversion ratio. We have 1 mole lithium hydrogen carbonate or lithium bicarbonate, both names work, 67.96 grams. And we can do a conversion for that. And then we have 1 mole of lithium hydroxide equals 1 mole of our product, lithium bicarbonate. And we can do a conversion for that. So now we're going to determine how much is produced. So we take our 50 grams, we do our molar mass, we do our balanced equation ratio of product to reactant, and then our molar mass for the product. And this produces 142 grams of lithium bicarbonate. So again, if you were confused about which one, percent yields usually give you they always, I should say always, but I always try to keep myself safe. They always provide the actual, and you have to determine the theoretical. If it's not, then it's worded really weird or something. But yes, it's always theoretical. You're trying to figure out, because see, here it was given, the actual yield was given. You have to calculate, and that's normally how these problems go. Just like limited reactants, they always give you the values of the reactants. Percent yields give you the given. You have to calculate the theoretical because you're not in the lab, so you can't say how much the actual is. So now we set this up, times it by percent, 72.8, 142. I told you the theoretical is always larger, and times it by 100, and the percent yield on this reaction is 51.3. So this means that this out of 100, this reaction produced 51.3 yield. So this is a low yield in lab. If you work in lab like I do, this is depending on the conditions. Though sometimes this is how reactions work. So reactions don't always go to 100%. In fact, they never do. But you try to improve the conditions. So for me, being in the lab, I would have to try to improve this yield by looking at other solvents, other stuff, to make sure to try to get this yield between ideally 70 and 80 is a good range. And this is the first thing people will ask, what was the percent yield? And this is saying that half of what we're doing here will get to the product, and half just goes on to something else. And that is it.